Hi, welcome to this second presentation about the best methods to alkylate amines. This video is about reductive alkylations of amines with aldehydes or ketones. This is one of the easiest and most common strategies for alkylating amines, and a huge number of variations and examples have been reported. I'll focus here on the most practical methods. The precise mechanism depends on whether a secondary or a primary amine is alkylated. The reductive alkylation of secondary amines must proceed by intermediate formation of an iminium salt or an enamine, which can be reduced by a number of different reducing agents. Primary amines can also form an intermediate imine, which is a weaker oxidant than an iminium salt and will require a stronger reducing agent to be converted into the alkylated amine. Because iminium salts are easier to reduce than imines or enamines, these reactions are often conducted under acidic conditions. This limits the scope of suitable reducing agents, as most hydride donors will also react with acids directly to yield hydrogen. These are some of the most common reducing agents suitable for the reductive alkylation of amines with aldehydes or ketones. If applicable, catalytic hydrogenation is usually the cleanest and most economic strategy for alkylating amines. A broad selection of heterogeneous or homogeneous catalysts can be used, and tiny amounts of catalyst are often sufficient. Unfortunately, many other functional groups can be hydrogenated too. And for amines containing alkenes, alkynes, nitro groups, acido groups, sulfur, or other reducible or chelating groups, a selective catalytic hydrogenation may not be possible. Then, some amines tend to form strong bonds to transition metals, in particular 1,2-diamines and related chelating groups, and can poison some catalysts. In such cases, strongly acidic reaction conditions may be helpful. Imines, enamines, and iminium salts can also be reduced by heating with formic acid, formate salts, or carbon monoxide. It is assumed that this so-called Leuckart-Wallach reaction proceeds by intermediate formation of radicals. This is also a practical, inexpensive, and clean way to alkylate amines, which generates only little waste. The main disadvantage is the high reaction temperature, which can cause a number of side reactions. Electron-rich arenes or heteroarenes, for example, may also be alkylated under the conditions of the Leuckart-Wallach reaction. One very popular method for the reductive alkylation of amines is the use of borohydrides as reducing agents. Sodium borohydride cleanly reduces imines, while cyanoborohydride or triacetoxyborohydride reduce iminium salts, but not aldehydes or ketones. Thus, these last two reducing agents can just be added to an acidified mixture of an amine and an aldehyde, and a high yield of alkylated amine will often be obtained. Unfortunately, these boron-based reducing agents are more expensive than hydrogen or formic acid and can only be used for preparing higher-priced amines. Then, occasionally, the product can form a strong bond to boron, in particular to cyanoborane, and these aminoboranes can be difficult to hydrolyze. Also, silanes can be suitable reducing agents for iminium salts, in particular in the presence of acids. These reagents are, however, expensive and not very selective, and offer no advantages if compared to boron derivatives or the other reducing agents on this list. Alkali metals or other main group metals have only rarely been used to reduce imines or iminium salts, but could, in principle, be an interesting alternative in special cases. These reactions proceed by single electron transfer, and pinacol-type dimerization is therefore a potential side reaction. Formaldehyde can act both as C1 alkylating reagent and as reducing agent. It has therefore been used to methylate amines, but arene alkylations are a common side reaction. The combination of formaldehyde with formic acid gives usually better results in the methylation of amines than formaldehyde alone. This is a recent example of enantioselective reductive amination of acetophenone with ammonia. Around 1% of a soluble catalyst and a number of additives were required, and the enantioselectivity wasn't very high. This is, however, a difficult reaction, and few examples of highly enantioselective alkylations of ammonia have been reported. As convenient alternative to ammonia for the conversion of ketones into primary amines, benzylic amines can also be used. Benzylic amines are easier to dose accurately and more basic than ammonia, and the benzyl group can be cleaved by hydrogenolysis under acidic conditions. In this example, one difficulty was to prevent racemization of the starting ketone. This could be achieved by keeping the reaction mixture acidic with a slight excess of titanium tetraisopropylate. Under these conditions, no enamine but only the imine was formed upon reaction with benzylamine. Hydrogenation in the presence of 0.6% of platinum on charcoal gave the desired cis-amine with high diastereoselectivity and only minimal racemization. After crystallization, the benzyl group was removed by hydrogenolysis with palladium as catalyst and in the presence of one equivalent of methane sulfonic acid. No hydrogenation of the phenyl groups occurred. Instead of benzylamine, enantiomerically pure alpha-methylbenzylamine may also be used as synthetic equivalent of ammonia. Both enantiomers of this amine are produced on a large scale by resolution of the racemate and are not very expensive. In this example, an enamine prepared from a beta-ketoester and alpha-methylbenzylamine was hydrogenated with high diastereoselectivity. Its toluene sulfonate salt was purified further by crystallization and debenzylated by hydrogenation in ethanol with palladium as catalyst. Primary amines can sometimes be alkylated sequentially with two different aldehydes or ketones. In this example, an alpha-amino acid ester was first isopropylated by catalytic hydrogenation in the presence of an excess of acetone. Because of steric crowding, no tertiary amine was formed. The intermediate, rather unreactive secondary amine could, however, be alkylated once more by catalytic hydrogenation in the presence of an excess of propanal, and a high yield of the tertiary amine was obtained, without any hydrogenation of the arene. A further convenient reducing agent for imines, enamines, or iminium salts is formic acid, and a number of variations of this reaction have been reported. The methylation of amines with a mixture of formaldehyde and formic acid is called Eschweiler-Clark reaction, an example of which would be the upper reaction on this slide. In general, reductions with formic acid require high temperature, usually above 100 degrees Celsius. The second example on this slide would be a methylation with formaldehyde alone. This strategy was successful in this instance, but usually gives more byproducts than the classical method with formic acid as reducing agent. If compared to methylations with a methyl halide, the main advantage of the Eschweiler-Clark method is that no quaternization of the product will occur. When anilines are mixed with formaldehyde and acids, a large number of different products can result. In this example, the methylation of nitroaniline proceeded as expected, but with more electron-rich anilines, many byproducts should be expected, resulting mostly from alkylation at the arene. These include, for instance, diaryl methanes, benzylic alcohols, benzylamines, and benzaldehydes. In this example, a sterically demanding secondary amine was alkylated with a number of different aldehydes and ketones using formic acid as reducing agent. Only the aldehydes yielded the expected tertiary amines, but not the ketones, probably because of steric crowding. Reductions with formic acid are particularly useful if the starting materials are not compatible with catalytic hydrogenation, as in the example on this slide. Bromoarenes or heteroarenes are readily debrominated during catalytic hydrogenations. Under optimized conditions, however, a clean reductive amination of 2-bromo-5-formylpyridine could be achieved with formic acid as reducing agent, without any hydrogenolytic or nucleophilic displacement of the bromine atom. The final product was obtained by a copper-catalyzed aromatic nucleophilic substitution of bromide by ammonia. At very high temperature, even amides may act as synthetic equivalents of amines. formamide alone or mixtures of formamide and ammonium formate can be used to convert even unreactive ketones into formamides, as in these two examples. Particularly impressive is the reaction of benzophenone, which is an exceedingly unreactive ketone that does not usually react with primary amines, not even under forcing conditions. Formamides are more readily hydrolyzed than most other amides and are therefore useful synthetic precursors of amines. In this example, DMF was used as synthetic precursor of dimethylammonium formate, suitable for the conversion of aldehydes or ketones into dimethylamines. This is an example of the use of sodium cyanoborohydride for the reduction of a glucose-derived iminium salt. Ammonium acetate was the acid providing for the formation of the iminium salt. As in alkylations with primary alkyl halides, ammonia also tends to yield secondary amines when alkylated with aldehydes. In this example, a huge excess of ammonia was used to prevent this side reaction, more or less successfully. In this optimized example, a secondary cyclopropylamine was alkylated with a protected form of cyclopropanone, again with sodium cyanoborohydride as reducing agent. Despite its sensitivity, a good yield of tertiary amine was obtained. In this example, the main problem was to avoid complete or partial reduction of the nitro group. This was best achieved with the borane amine adduct as highly selective reducing agent. In this instance, the imine was isolated and converted into an iminium salt by treatment with methane sulfonic acid. In this example, both the starting amine and the aldehyde were advanced, expensive intermediates, and none of them could be used in a large excess. With sodium triacetoxyborohydride, however, a high yield of the alkylated amine was obtained without any racemization or beta elimination of the amide. Some nitroanilenes can be methylated once by treatment with an excess of formaldehyde and sulfuric acid. In this example, no further alkylation of the arene or the benzoylated amino group occurred. The final product, a hair coloring agent, was obtained after debenzylation by sulfuric acid. So, what are the potential side reactions? Iminium salts and aldehydes are mild oxidants and can sometimes dehydrogenate amines. In this example, a norbornyl amine was extensively oxidized during an attempted Eschweiler-Clark methylation. Isopropylamines are particularly sensitive and prone to this side reaction. Although formates are usually quite selective reducing agents for imines, some ketones or aldehydes may also be reduced to alcohols under forcing conditions. In this example, 10% of a secondary alcohol resulted during a Leuckart-Wallach reaction in a glass-lined autoclave, but when a stainless steel autoclave was used, the alcohol became the main product. The high reaction temperature required for Leuckart-Wallach reactions can cause eliminations, substitutions, and a number of other unexpected reactions. Ketones with an alpha-methylene group, for instance, can be converted into pyrimidines when heated with formamide, as in this example. Such reactions can sometimes also be catalyzed by transition metals. As already mentioned, amines form rather stable complexes with borane and cyanoborane. Thus, after a reductive amination with borohydrides as reducing agents, the crude products should be treated with hydrochloric acid for some time, to make sure that all boron-nitrogen bonds have been hydrolyzed. This is not an example of reductive amination, but of the reduction of phenylalanine with borane. A mild, basic workup gave mostly an aminoborane as product. Its hydrolysis required treatment with 3 molar aqueous hydrochloric acid for 2 hours at room temperature. Some other potential side reactions include the hydroxyalkylation of arenes and the formation of diaryl methanes from the intermediate benzylic alcohols. Then, some functional groups are easily reduced, for instance olefins, alkynes, nitro groups, or acids. These may also react with some of the reducing agents required to reduce imines or iminium salts. Finally, heating ketones or aldehydes with bases and amines can bring about aldol condensations and Mannich reactions, or even the Cannizzaro reaction of reactive aldehydes. Thus, it is always a good idea to try to keep the reaction conditions as mild as possible. A huge number of reductive alkylations of amines with aldehydes or ketones have been described in the literature. On this and the next 2 slides, there's a short selection of some recent examples and reviews to give you an overview of the scope of this reaction and the most advanced procedures. You can also find these references in the description of this video. The next presentation is about the alkylation of amines with alcohols. In recent years, a number of catalysts have been discovered that allow these reactions to proceed under surprisingly mild conditions, and even complex multifunctional starting materials can be used with success. So don't miss it.